Swayam Prabha. Digital India. Educated India.
This is the third lecture on centrifugal compressor. Here I have solved some illustrative examples. I have solved here two problems. Let me state the problem number one. Here at a stagnation temperature of 22 degrees Celsius enters the impeller of a centrifugal compressor in the axial direction. The rotor, which has 17 radial vanes, rotates at 15,000 revolutions per minute. The stagnation pressure ratio between the diffuser outlet and the impeller inlet is 4.2, and the overall efficiency total to total is 83%. Further, the mass flow rate is 2 kg per second and the mechanical efficiency is 97%. It is also stated that the air density at the impeller outlet is 2 kg per meter cube and the axial width of the impeller is 11 mm. Assume the slip factor is given by sigma is equal to 1 minus 2 by z, where z is the number of radial vanes. Evaluate the following. A. The impeller tip radius and the power required to drive the compressor. B. The absolute Mach number at the exit of the impeller. So please note that it's a centrifugal compressor having radial vane. Here I have solved the problem. Before solution, I have derived here the expression for overall pressure ratio. Let us consider P01 be the total pressure at inlet to the compressor and P03 be the total pressure at exit, that is, exit from the volute casing. And if we express the compression process in TS diagram, then 1,3 represents the actual compression process and 1,3s represents the isentropic compression, and thereby I can write for a radial flow impeller H03 minus H01 is equal to P sigma U2 square, where P is the work done factor, sigma is the slip factor, and U2 is the blade speed at exit. From here, I can write T03 minus T01 is equal to P sigma U2 squared divided by TCP. T03 minus T01 represent the actual temperature rise during the process of compression. Let us consider eta C be the overall isentropic efficiency of the compressor. Then eta C can be stated as T03 S minus T01 divided by T03 minus T01. That is, isentropic efficiency is equal to the ratio of isentropic temperature rise to actual temperature rise. From here I can write T03S divided by T01 is equal to 1 plus eta C into T03 minus T01 divided by T01. Now T03 minus T01, I can put the value here by P sigma U2 square divided by Cp. Thus I can get T03S by T01 is equal to 1 plus eta C into P sigma U2 square divided by Cp into T01. Therefore, the overall pressure ratio can be related to this isentropic temperature ratio as P03 by P01 is equal to T03S by T01 to the power gamma by gamma minus 1 is equal to, within the bracket, 1 plus eta C into P sigma U2 square divided by Cp into T01 to the power gamma by gamma minus 1. Thus, this relation gives the overall pressure ratio in terms of isentropic efficiency of the compressor, work done factor, slip factor, blade speed at exit, and total temperature at inlet. So this is an important relation for centrifugal compressor. I have drawn here the schematic of a centrifugal impeller which is radial flow, thereby W will be in radial direction. Thus I have indicated here velocity triangle with and without slip at exit. The velocity triangle without slip is drawn by a form line, whereas the velocity triangle with slip has been drawn by the dotted line. Let me explain you the velocity triangle of a radial flow impeller. So let us consider the angular speed of the impeller is omega, and I have indicated the direction of the rotation, and U2 be the blade speed. So I have drawn U2 here. Without slip, the W2 will be in the radial plane. So I have drawn W2. So U2 plus W2 would be equal to C2. So this will be the C2. So this is the velocity triangle without slip. Now because of slip, W2 will slip back. So maybe slip velocity is Vs. Now if I draw the velocity triangle by red, which represents the slip, this is W2 dash. This will be W2 dash. This will be C2 dash. Thus I have indicated now the velocity triangle with sleep, which will be equal to U2 plus W2 dash is equal to C2 dash. Now, without sleep, C theta 2 would be equal to U2. So, without sleep, C theta 2 would be equal to U2. But C theta 2 dash is nothing but sigma into U2, where sigma is equal to sleep factor. Now, furthermore, if the compression process I can represent in HS diagram, this is the HS diagram where, as I have indicated, 1,3 is the actual compression and 1,3s be the isentropic compression. Now, if you come to the problem, the statements are T01 total temperature at inlet equal to 22 degrees Celsius, that is 295 K. Number of radial vane, which is denoted by Z here, is equal to 17. N is equal to 15,000 RPM, that is rotational speed. R, that is total pressure ratio, P03 by P01 is equal to 4.2. Isentropic efficiency, eta C is equal to 0.83. M dot mass flow rate through the machines, 2 kg per second. Mechanical efficiency eta M is equal to 0.97. Rho 2, density of air at exit, equal to 2 kg per meter cube. B2 is the width of the impeller at exit is 0.011 meter. Now I can write specific work small w, that is work done per unit mass flow rate, is equal to 803 minus 801. 803 is the total enthalpy at exit of volute casing. That must be equal to 802. That means total enthalpy at the exit of the volute casing must be equal to the total enthalpy at exit of impeller, since there is no work done within the diffuser and the volute casing. Thereby, small w, which is the specific work, is equal to 803 minus 801 is equal to 802 minus 801, where 802 minus 801 must be equal to U2 into C theta 2, being C theta 1 is equal to 0 for radial flow machine. Now I have told C theta 2 would be equal to sigma into U2. So small w would be equal to sigma into U2 square. Thus I have indicated earlier pressure ratio P03 by P01, that is denoted by smaller, is equal to, within bracket, 1 plus eta C sigma U2 square divided by Cp into T01 to the power gamma by gamma minus 1. Now, from here I can represent U2 as U2 square is equal to Cp into T01 within bracket R to the power gamma minus 1 by gamma minus 1 divided by sigma into eta C. Now, sigma is equal to 1 minus 2 by Z, Z being the number of vane, that is equal to 1 minus 2 by 17. This would be 0.8824. Thus, I have evaluated sigma as 0.8824. Now, following the earlier derivation, U2 square would be equal to Cp, that means 1005 into T01, that is 295, within the bracket R to the power gamma minus 1 by gamma minus 1, that is 4.2 to the power 0.286 minus 1 divided by sigma into eta C. Sigma that I have calculated as 0.8824, eta C is given as 0.83. Thus, as I have evaluated, I've got U2. U2 is equal to 453.2 meter per second. Now, rotational speed omega is equal to 2 pi n by 60. I know n, that is 15,000 rpm. Thus, omega is equal to 1570.8 radian per second. Now, U2 must be equal to RT into omega. Thus, I can evaluate RT as U2 by omega. I have substituted the value of U2 as 453.2 and value of omega as 1570.8. So RT would be equal to 28.85 centimeter. Thus, I have got the value of tip radius. After evaluating the impeller outlet radius, let us calculate the actual shaft work as W dot actual would be equal to W dot divided by eta m. This W dot would be equal to m dot into small w divided by eta m. Small w being the specific work input, which would be equal to sigma into U2 square. Thus, W dot actual would be equal to m dot sigma U2 square divided by eta m being the mechanical efficiency. Thus, put all the value 2 into 0.8824 into 453.2 square divided by 0.97 divided by 1000. That means we have converted to kilowatt. So thus W actual, that means actual shaft work, is 73.7 kilowatt. So this is the another answer. Now the absolute exit Mach number M2 would be equal to C2, that is absolute velocity at exit, divided by A2, that is local sonic speed. That is equal to C2 by root over gamma R T2. Now from the velocity triangle, C2 is equal to root over C theta 2 square plus CR2 square. Now CR2 is equal to m dot divided by rho into A2. A2 is the exit area of the impeller. Now m dot, the value of m dot is given. Now, okay, let me write down the expression CR2. It would be m dot divided by rho 2 into pi r T2 into B2. Instead of tip radius, it is better to say impeller exit radius. So RT being the impeller exit radius. Now I know all the values here. So I can calculate CR2, thus putting all the values, right, as stated here. So if you evaluate CR2, we will get CR2 as 50.15 meter per second. Now C theta 2 would be equal to sigma into U2. Put the values of sigma as 0.8824, U2 as 453.2. So if you multiply this, you will get about 400 meter per second. Now C2 can be stated as root over C theta 2 square plus CR square from the rectangle. Thus it would be root over 400 square plus 50.15 square. So I got the value of C2 as 403.13 meter per second. Now I can write 802 is equal to 801 plus W, where 802 is equal to enthalpy of fluid at the exit of the impeller. 801 is the total enthalpy at the inlet, plus small w is equal to specific work input. Now here 802 I can write as H2 plus half C2 square. Thus I have written as H2 is equal to 801 plus small w minus half C2 square. Furthermore, H2 I can write Cp into T2 and H01 as Cp into T01. Thus I can write T2 is equal to T01 plus omega. Omega is the specific, or small w is the specific work, minus C2 square by 2 divided by Cp. Now let me evaluate small w, that is specific work input, is equal to sigma into U2. I know the value of sigma. I know U2, that is equal to 453.2. So I have converted it to kilowatt divided by 1000. So it will be 181.23 kilowatt. Note that this will be there is some typing mistake. This will be square. Now after evaluating small w, you put all the value here. So T01 is 295, small w here 181230, minus this is C2 403.13 square divided by 2 divided by 1005. So this is 295 plus 99.5. It would be 394.5. Thus, exit temperature I have evaluated as 394.5. The same would be equal to C2 divided by root over gamma T2. So I know all the values. C2 as 403.13 root over 1.4 287 into 294.5. It will be equal to 1.0125. Thus exit Mach number is equal to 1.0125. The second problem is on the diffuser of a centrifugal compressor, that the problem statement is air enters the diffuser of a centrifugal compressor with a velocity of 300 meters per second at a stagnation pressure of 200 kilopascals and a stagnation temperature of 200 degrees Celsius, and lifts the diffuser with a velocity of 50 meters per second. Using the compressible flow relations and assuming the diffuser efficiency eta D equal to 0.9, determine A. The static temperature and inlet and exit of the diffuser and the inlet Mach number. B. The static pressure at diffuser inlet and exit. C. The increase in entropy caused by the diffusion process, given gamma equal to 1.4 and Cp is equal to 1005 joule per kg per K. The fluid is diffused in a diffuser without addition of any external energy. Hence, the diffusion process can be represented in HS diagram here, where P1 be the pressure at inlet to the diffuser as the temperature is T1, and the fluid enters the diffuser with a velocity C1. Similarly, P2 and T2 be the pressure and temperature of the fluid at exit to the diffuser, and C2 being the velocity at exit. Thus, in HS diagram, I have plotted the constant pressure line P1 and P2, and 1, 2 be the process, which is the diffusion process, and non-isentropic process, the entropy increases. Here, however, I can say H01 is nothing but H1 plus C1 squared by 2 must be equal to H02, which is equal to H2 plus C2 squared by 2. Thus, I have got P01 and P02 line. Considering a isentropic line, I have got the point 2s and 0 2s. So this is the diffusion process in the TS diagram, and or you can say the diffusion process in the HS diagram, and thereby I can say the diffuser efficiency as eta D is equal to T2s by T1 minus 1 divided by T2 by T1 minus 1. Now, the point T2s is given by here, which represents the isentropic temperature rise in the diffuser. From energy equation, I can write H01 minus H1 is equal to C1 squared by 2, thereby Cp into T01 minus C1 is equal to C1 squared by 2, and hence T1 by T01 is equal to 1 minus C1 squared divided by 2 Cp into T01. C1 is given as 300 meters per second and T01 as 473 Kelvin. Thus, T1 by T01 is equal to 1 minus 300 squared divided by twice 1005 into 473. If you compute this, you will get 0.9053. T01 is given as 473, thus you can evaluate from here T1 as 428.2 Kelvin. Now Mach number at inlet to the diffuser can be stated as M1 is equal to C1 by root over gamma RT1, where gamma RT1 is nothing but local sonic speed. Now, so E1 can be evaluated as root over 1.4 into 287 into 428.8. So I have got A1, that's local sonic speed, as 414.8 meter per second. Thus M1 is equal to C1 by A1. So A1 I have got as 0.7233. Thus I have evaluated T1 and M1, that is temperature, static temperature inlet and inlet Mach number. Now I'll have to evaluate static temperature at exit to the diffuser. Now again, applying energy equation at exit, I can get H02 minus H2 is equal to half C2 square. Thereby T2 by T02 is equal to 1 minus C2 square divided by twice Cp into T02. Now T01 must be equal to T02, that is equal to 473. C2 is equal to 50. Thus T2 divided by T02 is equal to 1 minus 50 square divided by 2 into 1005 into 473. So if you evaluate that, you will get 0.9974, and hence you can get T2 as 471.7 Kelvin. Thus I have got exit temperature of fluid as 471.7 K. From the expression of the diffuser efficiency, we can write T2S by T1 is equal to eta D within bracket T2 by T1 minus 1 plus 1. Now eta D is the diffuser efficiency. We have already evaluated the value T2 and T1. Hence T2 S by T1 is equal to 0.9 within bracket 471.7 divided by 428.2 minus 1 plus 1. If you evaluate this, you will get 1.0915. Now P2 by P1 I can relate with respect to T2S by T1 through isentropic relation. Look here, P2 by P1 can be related with respect to T2S by T1. Thus I can write P2 by P1 is equal to T2S by T1 to the power gamma by gamma minus 1. That is equal to 1.0915 to the power 3.5. So P2 by P1 would be equal to 1.3588. Similarly, P01 by P1 is equal to T01 by T1 to the power gamma by gamma minus 1. Now T01 I know as 473 and T1 as 428.2. Thus P01 by P1 is equal to 473 divided by 428.2 to the power 3.5. That would be equal to 1.4166. Now P1 would be equal to P01 divided by 1.4166, that is equal to 200 divided by 1.4166. It will be equal to 1 for 1.2 kilopascals. The value of P01 is giving us 200 kilopascals. So I have evaluated the value of static pressure at inlet, P1. Now from this ratio, P2 by P1, I can now evaluate P2. So P2 would be equal to 1.3588 into P1, that is equal to 141.2, that will be 191.8 kilopascal. Thus, I have evaluated also P2. So whatever has been asked, I have calculated here, except increase in entropy due to the diffusion process. How that can be calculated? From thermodynamic relation, we know T into ds is equal to dH minus 1 by rho into dP. Thus I can get ds is equal to Cp into dt by T minus R into dP by P. If we integrate between 1 and 2, I'll get S2 minus S1 is equal to Cp into ln T2 by T1 minus R ln P2 by P1. Now I know all the values here. Thus I have got 1005 ln 471.7 divided by 428.2 minus 287 pressure ratio P2 by P1, that is ln 1.3588. If you evaluate this, you will get 9.2 joule per kg per K. Thus, I have also evaluated increase in entropy, which is equal to 9.2 joule per kg per K. Thus, answer is the static temperature at inlet and exit of the diffuser as T1 428.2 Kelvin and T2 is equal to 471.7 Kelvin. You please appreciate increase in temperature. And what is the Mach number at inlet is 0.7233. Furthermore, the static pressure at inlet and exit P1 as 141.2 kilopascals, P2 is 191.8 kilopascals. So please appreciate the increase in static pressure because of the diffusion process. Furthermore, since the diffusion process is a non-isentropic process, because there will be an increase of entropy during the process, and thus del S is given by 9.2 joule per kg per K. Thank you for listening. I'll request you to solve similar problem on centrifugal compression.